So, welcome back to the lecture series on fundamentals of air pollutions. In this lecture, we are going to discuss the basic laws that govern the climate change, are the radiations that we are getting on the Earth's surface, what are the factors that are affecting the radiation, what are the different terminology that we use in the electromagnetic radiation, and then what kind of actually properties electromagnetic radiations have. So, this will be a kind of first lecture will be a very basic lecture, and then we will talk about the Planck's law, Stefan-Boltzmann law, then Wien's displacement law, and all the 4 laws that are there actually we will discuss in this lecture. Okay. So, if you see what is electromagnetic radiation? Electromagnetic radiation is the energy. So, actually if you see it, electromagnetic radiation is an energy that propagates through the space as oscillating electric and magnetic field, okay, and it is moving at the speed of the light c, which is actually 3 into 10 to the power 8 meter per second. So, if you just see this one, all the electromagnetic radiations, they are moving at a speed of light. So, you can actually or you can also define electromagnetic radiation as a form of energy that is generated when electrically charged particles move through matter or a vacuum. So, now this is very important. This is the energy generated when electrically charged particles. So, this is actually very important, and this is the electrically, because of the electrically charged particles, this electromagnetic radiation gives energy, and it can also produce, and because it is an electrically charged particles, it can it will be able to give you electric field, okay, it will generate electric field, and because it is moving, it will be able to have a magnetic field. So, all the electric and magnetic field is just because of the charged particles, okay, and thus alternatively it can be also produced by oscillating magnetic and electrical disturbance. So, even if you do not have charged particle, and if somehow can create a oscillating magnetic and electric field, you can also produce electromagnetic radiations. So, the examples of electromagnetic radiations are visible light, that light we see through our eyes, radio waves through which we hear the songs, and then microwaves, and then X-rays. This is very important. Some of the things are there actually. We do not have all the things here. If you just want to see, we have in the next section. So, have you ever wondered why we could see colors, why the sky is blue, and why or how the sun's radiation reaches on the Earth's surface? And this is all actually lies in the definition of the electromagnetic radiation. So, we will discuss some of these opening questions that are there. So, as I said that it is actually like electromagnetic waves kind of things are there actually. So, light is actually dual property. We all know that light can have actually dual property. So, it can have actually like wave, and it can also like act as particle. So, it shows a dual characteristics, and here the particles wave nature is shown. So, because this is actually there will be a magnetic field and electric field. Just to note that electric field and magnetic field, they are perpendicular to each other. So, this is actually very important to remember. And then as I said that particles behaves like both waves and particles is actually example of photon, and the energy, and this is because we are now relating the energy, and energy is will be, and when we are talking about the wave, then you will have a wavelength GTH. So, say you have wavelength lambda, or this can be calculated into 1 upon lambda, and then you have frequency, okay, and this is actually when you treat particles, then it means this will have energy, and this energy is given by hc upon lambda r h into nu. So remember this one, that this energy is energy that photon of wavelength lambda has. Actually, here one thing is very important to remember, that the energy is directly proportional to the frequency. So higher the frequency, this means higher the energy, but the energy is actually inversely proportional to the lambda. So this is very important. Lower wavelength photons, they will have high energy compared to the higher wavelength. So just remember these things, otherwise it will be very complicated. And h is actually Planck constant, c is speed of light. So you can see this energy is totally dependent on lambda only. So hc upon lambda, h becomes Planck constant, c becomes, and this is actually like Planck constant, E is actually 6.63 into 10 to the power minus 34 joule second, and this is called Planck's constant. Okay, and c we have already defined is actually like 3 into 10 to the power 8 meter per second. So you can multiply these numbers and you will be able to calculate the energy. Also remember that sometimes the energy is given in joules, sometimes energy is given in electron volt. So the conversion of these two, you must be knowing this one. So and then lambda is the distance between the two waves crest, like here you have this one and then here. So this is lambda, okay, from here to here. So this is lambda, you have lambda by 2. So any two positions you can define this one. And then wave number of the wave cycles per second. So frequency is actually number of wave cycles per second. So you can remember these numbers, and if you just remember here, E is equal to hc upon lambda. So h is actually 6.63 into 10 to the power minus 34 into c is 3 into 10 to the power 8. And of course you always write units, joule second and meter per second. So second will go here, and joule is watts per meter square. So this will be actually kind of, you just multiply with these numbers, you will be with 3 3 9, 3 6 18, 3 6 18 19, okay, 19.89 into 10 to the power. This will be like 34 and 8, 26 minus 26. We will come to this one again, and this becomes, this is actually a constant, and this divided by lambda. So you will have the energy itself. And lambda, note down that lambda is, because this is actually unit is in meter, then lambda you have to report in meter, otherwise you will always be getting a wrong answer. So just remember the units that you are going to use. Okay, this is what electromagnetic spectrum here we have, and you can see shorter wavelengths, they are squeezed here, and then shorter wavelength means they will be high energy intensity, and as you move further you will have longer wavelengths, so you have lower energy intensity. And then you can start all the way, the radiation that we talk about is right from the gamma rays, X-rays, ultraviolet, infrared, microwave and radio waves. So the way I used to remember this one is this is gamma, X, of course I wrote A, but just to remember X means I have used A here. So gamma ray, X-ray, UV, and then you have visible, and then you have R, and then you have Hertzian wave, okay, microwave and radio wave, then you have later on. So this is actually very important. And if you want to see important thing here is that, since we will be talking about the energy from the sun, there are two things, that our sun radiates electromagnetic energy as a black body. So sun is actually treated as a black body, and with the average temperature of about 5800 Kelvin. So sun's surface temperature is already about 5800 Kelvin. So this is at very high temperature. And just to remember another few points, that about 99% of the energy of the solar radiation falls in the narrow bandwidth of electromagnetic radiation between 200 to 2600 nanometers. So about because our sun is emitting all the radiations right from gamma to radio waves, but if you see that energy, 99% of energy is actually between, so you can see here this is like this will have all the energy. So considered by if you just take about almost all the energy is here, then you have very little about this one, infrared and then microwave and radio wave. So just remember about 99%, 99.9 or almost 100% is actually between 200 to 2600 nanometers. And solar energy is light. So we also know, this is also very important, that solar energy is actually, you can treat as a light and heat, and we can convert those photons of light energy into electricity. So you can either way, you can just use this solar energy, and this is actually like photo electric effect that we call it, and that's how the solar panel works. So you can convert those photons of light energy into electricity. And if you just calculate the solar radiation that is reaching on the earth surface is about 1360 watts per meter square, we call it actually irradiance. We will talk about this one, there is actually different terminology, so we will be talking about this one. Yeah, so if you see in the previous slides I said that it is about 5800, 5900, sometimes 5800, it was 800 Kelvin, so sometimes you have 5900 or sometimes it is written as actually 6000 Kelvin. So just these are the numbers you have to just remember. And if you have an ideal black body, okay, the curve will look like this one, LO1, this curve will look like this, and it will be peaking somewhere around 500 nanometer. Again remember that this peaks at around 500 around the blue light, okay. And if you just see that what is the irradiance, I told about that irradiance, that the irradiance is the energy that is falling on the top of the atmosphere of the earth surface. This is the measured one, so you will see lots of little bit kinks and ups and downs in this one. So this is because the energy is absorbed and other things. And when the irradiance, you talk about the earth surface, how much actually on the earth surface, we are talking about the earth top of the atmosphere, where the other things in the atmospheric compositions like water vapor, clouds, and then carbon monoxide, and then ozone, all those are not present, then you have this kind of radiance. And you see there are many peaks, again peaking up here at the surface, and some of the absorptions are very strongly absorbed, some are actually like are opaque. So you can see this one, and if you see here the stars say around 200 nanometer and about say 2600 nanometer or so, this peak is gone, almost you have completely the irradiance that is there is almost reduces to 0. And you remember this one, I will discuss more. The unit of irradiance is watts per meter square per nanometer, and since this is a curve, so what you do, you have watts per meter square nanometer, and when you integrate this curve, okay, so you will have something like you have wavelength multiplied by meter, so this will be going out, and then you will be having watts per meter square, and this is called actually radiance. Okay, so the radiance in the previous I think I just talked about, this is actually radiance, this is not irradiance. When you say this is, so this is radiance because you have not taken per unit wavelength, so this will be radiance. There is a huge confusion, and I also get confused with this one, but I will give you some tricks that how to remember those things. And so as I said, that sun emits all the wavelengths of light, and light from the gamma ray to Hertzian wave or radio wave and microwave, but the solar radiation that reaching Earth's ground is mostly confined in 300 to 2500 nanometer, and this is actually like 99.9% of the solar radiation is between falling in this one. So if you integrate all the radiation in this wavelength, you can be able to get almost like complete radiation. And out of this, If you talk about, this is ultraviolet radiation less than 380 nanometer we talked about, and the energy that is actually out of 100%, if I take solar radiation, then 3 to 5% is because of the ultraviolet radiation, and then you have like visible about 380 to 780 nanometers. You have about 40 to 45%, 40 to 43% is sun's radiation is actually, and then you see this is actually the peak that is already there. Okay, so this peak you can already see for the, okay, so in the visible spectrum you see most of the radiation that is there actually. And when you talk about the more than 780, here you have infrared, about 52 to 53% is actually, and this is mostly in the form of thermal energy. So these are the three wavelengths, ultraviolet, visible and infrared. They are very important for us. Okay, so now having said that, we now have some idea that our sun is actually black body. Its surface temperature is around say 5900 Kelvin. Okay, so what will be the energy that is emitted from the sun's surface? So sun's surface, the energy will be emitting, it will be given by sigma T to the power 4, and this is actually Stephen Boltzmann law, and this we will discuss in details. So the energy from the sun will be given by the Stephen Boltzmann law. And what is the energy when you do this one, energy from the sun over time? You see like if you want to see this one q or dq, and you see over time delta t or dt. So this is actually flux. Flux is nothing but dq by dt. Okay, so this you remember. And when you tie this flux over the detector area, when what area this is falling, actually this becomes irradiance. So you have dq by dA and dt, this becomes irradiance. And when you actually talk about in the given interval, then it is called monochromatic irradiance. Okay, so this will be actually like dq by dA, dt and d lambda. This will be actually monochromatic radiance. And again, if you just talk about the over the solid angle on the earth, what is the irradiance that is falling on a particular given solid angle? So this will be actually dq by dt, dA and d omega. This will be called as actually radiance, and this radiance is actually observed by satellite radiometer. This is actually what satellite observe when the radiation that is falling on this one, and this radiance is described by the Planck functions. We will see in coming slides, and this Planck function can be converted into brightness temperature, and that's how how the bright sun or stars are, if you just talk about then the galaxy term. So this is you have to just remember that these are the different terminologies. So what is actually, every terminology is important, and you will always have one or two objective questions from this one, that what will be the unit of this one, or which is the perfect graph or right graph. So remember this, I just use the term called ephemer, and this is actually just for myself, remembering myself. I just put E is actually energy, F for flux, I for irradiance, and then Mi actually is for monochromatic irradiance, and then R is actually for the radiance. So if you just remember these terms, if you need, you will be able to calculate these things if you understand this. So if I just see this again, the terminology and with their units actually, so energy from the sun is actually, if you just represented by dq, this unit will be given in joules, and if you calculate what is the energy that our sun is emitting, actually is somewhere around 1.2 into 10 to the power 44 joules. It's huge energy that our sun is actually emitting or having. And then if you just calculate dq by dt, it will becomes flux. Okay, and then the unit will be joule per second. So this means joule per second is watt. So you can calculate this one. So what is the flux? Flux will be 3.9 into 10 to the power 26 watts. So we will be able to calculate this one also. You have to take care of that how what is the sun's life actually, and then other things, time, because time is there actually. And if you just talk about dq by dt by dA, it will be irradiance, and it's the unit because of this one. Dq by dt has a unit of joule, so sorry, watts, so the unit will be watts per meter square, and this is generally written Wm to the power minus 2 or W upon mod m square. And if you calculate the irradiance from the sun is about 6.34 into 10 to the power 7 watts per meter square, and when we calculate that what is the irradiance that is reaching at the earth's surface, it's about 1380 watts per meter square. So you see there is a huge reduction in the energy. Okay, and if you just calculate this one monochromatic irradiance dq by dt by dA by d lambda, then the unit will be watts per meter square per micron. You can also correlate because wavelength and frequency are inversely related, so you can also write watts per meter square per centimeter. And then radiance, when we talk about, it's dq by dt by dA, d by d lambda and d omega. This is actually steradian, so watts per meter square per micron per steradian. This will be the unit of kind of radiance. Okay, so again I told that this energy 1.2 into 10 to the power 44 joules that is there is because of it's for the entire life of the sun. So if you assume that what is the life of the sun, then how much energy it would be actually stored. Okay, we will see this one in coming slides. So the next thing is actually radiation from the sun we talked about. So energy transfer, the rate of energy transfer by electromagnetism is called radiant flux. So we already talked actually that how much actually energy is there in the sun, and the rate to which the energy is transferred. So you have dq by dt is actually called flux, which has a unit of energy per unit time, and it is denoted by F is equals to dq by dt. And if you calculate the radiant flux from the sun is about 3.9 into 10 to the power 26 watts. Okay, and from here if you want to calculate the time of the sun, so you can calculate 1.2 into 10 to the power 44 okay joules, and then you have 3.9 into 10 to the power 26 watts joule per second, watts na. This is the actually the energy that we will be having flux dq by dt. Watts means joules per second, so joule will be cancelled out. You can calculate 1.2 and 3, so it will be 0.4. You can calculate 0.3. Okay, you just roughly take 4 this one, and then it will be actually 10 to the power 26, 8, 34 and 18. This much second will be life of the sun, and you can calculate that how many numbers of years the sun life is there. It's very huge number. Okay, the next terminology I talked was irradiance. So now we are done with energy, we are done with the energy, we are done with the flux now, and from the flux we talk about irradiance. Okay, the irradiance is radiant flux per unit area. So you remember here radiant flux is actually dq by dt, and this is per unit area, means if you take dA, so dq by dt by dA is called irradiance, and or sometimes it is radiant flux density. So you remember the terminology is very important, and if you just mix up somehow the terminology, it will be very difficult for you. So just remember that these terminologies are very different actually. Okay, you stick to a terminology, or you just remember the terminology. So you can be written as dq by dt by dA, and the unit will be watts per meter square as we talked about. Okay, now you have to see this one. Irradiance from the passing through the outermost limit of the visible sun disk, and if you assume the radiation Earth's radius of the sun surface, radius of the sun is actually 7 into 10 to the power 8 meter. So this will be actually like the surface area will be 4 pi r square, and you can calculate 4 pi into 7 into 10 to the power 8, this much meter square. This will be the surface area through which the radiation is passing through. So you have already 3.9 into 10 to the power 6 radiant flux, and then 4 pi 7 into 10 to the into 7 into 10 to the power 8 ka whole square, you will get actually 6.3 into 10 to the power 7 watts per meter square. This is what is remember in the lecture I talked about 6.34 into 10 to the power 7 watts per meter square is the radiance that is emitted by the sun, and when it reaches to the earth's surface you can calculate, and in the coming slides we can calculate that how much is actually the radiation that is reaching at the earth's surface. So similarly, because this radiation is passing through the distance, so sun and earth distance is about 1 astronomical unit. So this means 1.5 into 10 to the power 8 kilometers. So when it travels through this distance, how much energy can be actually reached? So we can calculate that one as well. And so if you just remember this one, terminologies are very important here. And the different terminology: energy, flux, irradiance, monochromatic irradiance. And this is if you just are asked that in the graph, what is the unit of y-axis? Okay. So for example, in the previous class, if you remember here, this is actually if somebody is asking that what is the unit or what is the physical parameter that is plotted here, it is irradiance. And then if somebody is asking whether the units, so you should remember, because it becomes the area under the curve become the kind of total energy that is emitted by the surface. So watts per meter square. So you can integrate this energy. In fact, if you see it's like it reaches from 0 to 2 point, about maximum is 2, somewhere around irradiance is 2, and maximum wavelength is actually somewhere around blue wavelength. So these are the two very important parameters that in the usually when we have to calculate, we usually plot this as a irradiance versus the wavelength, and sometimes this becomes, because this is very important, you have to integrate the energy, the wavelength is actually varying, so you have to see this one, that lambda is there, so d lambda you have to do the integration. Okay, so just remember this one, and you also remember this terminology. This is very important when you are actually going to study about some of these things. You should also remember, I told about that how to remember this terminology, like ephemer, energy, flux, irradiance, monochromatic irradiance, and then radiance. And then this is actually like what is the satellite. So for example, somebody asks is what is the physical property satellite radiometer is observing? It's irradiance or radiance. So it is actually, because you are talking about the solid angle, so you have already calculated the solid angle, so this means you have taken care of solid angle, so this means this will be radiance. So radiance is measured by the satellite radiometer, but when we see the energy that is measured, it is usually irradiance, and this satellite's radiometer, and then this is described by the Planck's law or brightness of the temperature. So just remember this one. We will do some calculation again in this lecture, and which will be very helpful to you. So yeah, I think we have discussed about the energy, flux, and irradiance. In the next lecture we are going to discuss about the monochromatic irradiance, and then we will also discuss radiance, and we will see some of the physical equations, physical laws which are governing the climate change and then the energy from the sun. So thank you very much.